The flying car, a concept once confined to science fiction, is no longer a distant dream. It's taking shape right now in aeronautical labs around the world, and it's called the eVTOL. Welcome to G Fun Facts Online. Today, we're diving deep into the engineering behind these electric vertical takeoff and landing aircraft, the machines set to launch a new era of urban air mobility. The vision is to have sleek, quiet, emissions-free vehicles lifting off from city rooftops, bypassing traffic to get you across town in minutes. Companies like Joby Aviation, Archer, and Lilium are racing to make this a reality. The UK government is even targeting the first piloted flying taxi flights by 2026. But how do you actually build a car that flies? The answer lies in a combination of revolutionary engineering breakthroughs. The single most defining feature of an eVTOL is its electric propulsion system. Unlike helicopters or airplanes that rely on noisy, complex combustion engines, eVTOLs use multiple electric motors. This is a game changer, not just because it's cleaner and quieter, but because it allows for a radical new design philosophy called distributed electric propulsion, or DEP. Instead of one or two large engines, DEP spreads many smaller electric motors across the aircraft's frame, usually along the wings. This distribution of thrust provides incredible advantages. It enhances flight efficiency, gives pilots finer control, and, most importantly, creates massive safety through redundancy. If one motor fails, or even a few, the others can compensate, allowing the aircraft to continue flying and land safely. This principle is the cornerstone of the safety case for eVTOLs. This design freedom has led to a fascinating variety of aircraft. The simplest design is the multicopter, which looks like a giant drone. It uses multiple fixed rotors for all phases of flight. A great example is the EHang 216S. It's mechanically simple and very stable when hovering, but it's not very efficient for flying long distances, limiting its range to about 35 kilometers. Then you have the Lift Plus Cruise design. These aircraft have two separate sets of propellers, one set for vertical lift during takeoff and landing, and another set for forward thrust during cruise. The lift rotors shut down once the aircraft is flying forward. This allows each system to be optimized for its job, but the deactivated lift rotors can create drag, which reduces efficiency. But the most popular and versatile designs fall under the category of vectored thrust. These aircraft use the same propellers for both vertical lift and forward flight by physically tilting them. The most common type is the tilt-rotor. Joby Aviation's S4 and Archer Aviation's Midnight are perfect examples. The Midnight has 6 propellers on its wing. For takeoff, they point upwards like a helicopter. Once airborne, they tilt forward to propel the aircraft like a plane. A variation is the tilt wing, where the entire wing section rotates with the propellers. And then there's Lilium's unique approach. Their Lilium jet uses 36 small, ducted electric fans embedded in its wings. These ducts improve aerodynamic efficiency and, crucially, make the aircraft much quieter. Lilium calls this ducted electric vectored thrust. These vectored thrust designs offer a great balance of hover capability and high-speed forward flight. But managing the complex transition between vertical and horizontal flight is a major aerodynamic and software challenge. Powering this revolution are incredibly advanced electric motors. The most common are permanent magnet synchronous motors, chosen for their high efficiency and power density. Then there are brushless DC motors, which are simpler and more cost-effective. But the real buzz is around axial flux motors. Unlike traditional motors, their unique pancake-like shape delivers exceptionally high torque and power for their size and weight, making them perfect for eVTOLs. But if electric propulsion is the heart of the machine, then the battery is its Achilles heel. This is arguably the single greatest engineering challenge. Jet fuel is incredibly energy-dense. It packs a huge amount of energy into a very small mass. Today's best batteries don't even come close. For a typical urban air taxi mission, It's estimated that a battery pack needs a specific energy of around 380 to 460 watt-hours per kilogram. For comparison, the battery cells in a high-end Tesla are around 260 watt-hours per kilogram. Current generation batteries can handle short demonstration flights, but a major leap is needed for commercial viability. This problem is made worse by the fact that an eVTOL's battery weight is constant. A plane gets lighter as it burns fuel, but an eVTOL has to land with the full weight of its depleted batteries. This is why the world is in a race to build better batteries. The holy grail is the solid-state battery. These replace the flammable liquid in today's lithium-ion batteries with a solid material. This not only makes them safer, eliminating the risk of fire, but also promises much higher energy densities. Another promising technology is lithium-sulfur batteries. They have a much higher theoretical energy density and use cheap, abundant sulfur. NASA's SABRES project is working on this, combining a lithium-sulfur design with a solid-state electrolyte, and they've already achieved energy densities over 500 watt-hours per kilogram in the lab. Some companies are also looking at hydrogen. In June 2024, Joby Aviation tested a modified aircraft with a hydrogen electric system where a fuel cell recharges the batteries in flight. They completed a staggering 523-mile flight, proving a potential pathway to much longer ranges. Beyond just storing energy, there are two other critical battery challenges: heat and charging speed. The immense power required for takeoff generates a lot of heat. This requires sophisticated thermal management, like liquid cooling systems, to prevent batteries from overheating and degrading. For an air taxi service to be profitable, aircraft need to be in the air, not on the ground charging. The goal is to recharge a battery in just 5 to 10 minutes. This requires megawatt-scale charging infrastructure, a huge challenge for both the batteries and the electrical grid. To tackle this, major players like Vertical Aerospace and Archer are adopting the Combined Charging System, or CCS, creating a standardized plug for the entire industry. Of course, all this technology needs to be housed in an airframe. In aviation, every gram counts, and for eVTOLs, this is an obsession. The airframe must be incredibly strong yet feather-light to maximize range. This is where advanced composite materials come in. Carbon fiber reinforced plastics, or CFRPs, are the material of choice. They are stronger than steel but lighter than aluminum, and they can be molded into complex aerodynamic shapes. Different composites are used for different parts, from toughened resins for the main structure to high-temperature thermoplastics for rotor blades. Other materials are also in the mix. Thermoplastics are gaining traction because they can be easily reformed and are well-suited for 3D printing, potentially lowering manufacturing costs. These materials also play a key role in making eVTOLs quiet. A low-noise footprint is critical for public acceptance in cities. Besides quieter electric motors, noise is managed by integrating acoustic damping materials, like honeycomb structures, directly into the airframe. The manufacturing process itself is also being reinvented. Traditional aerospace manufacturing is slow and labor-intensive. To build thousands of eVTOLs, the industry is borrowing from automotive, moving towards high-volume automated production. Techniques like automated fiber placement use robots to precisely lay down carbon fiber tapes, while 3D printing allows for the rapid creation of complex, lightweight parts with minimal waste. Now for the brains of the operation: the flight control and autonomous systems. The dynamic flight of an eVTOL, especially that tricky transition from vertical to horizontal flight, is far too complex for a human to manage directly. That's why these aircraft are built on fly-by-wire technology. The pilot's controls aren't mechanically linked to the motors and surfaces. Instead, they send digital signals to a flight control computer. The computer interprets these inputs and commands the aircraft, but it also has a flight envelope protection system. This means the computer won't let the pilot make a maneuver that would put the aircraft in an unsafe state. It simplifies flying and dramatically increases safety. But the long-term vision is full autonomy. Removing the pilot saves weight and cost, which is crucial for making these services affordable. Achieving this requires a symphony of advanced sensors. Autonomous eVTOLs will use a combination of LiDAR, radar, and high-resolution cameras to build a 360-degree picture of their environment. AI algorithms will process this torrent of data in real time to navigate and make critical decisions. A key piece of this puzzle is the detect and avoid system. This allows the aircraft to spot and steer clear of other aircraft, drones, birds, or even a new construction crane that wasn't there yesterday. Companies like Wisk Aero, a subsidiary of Boeing, are focused on autonomy from day one. Their goal is to certify a fully self-flying air taxi. With thousands of these aircraft potentially flying over a city, you can't just rely on traditional air traffic control. A new automated system called Urban Air Traffic Management, or UTM, is being developed. Think of it as a digital highway system for the sky, creating flight corridors, tracking all vehicles in real time, and providing weather and obstacle data to ensure everyone stays safely separated. The success of eVTOLs also depends on what happens on the ground. These aircraft will operate from new infrastructure called vertiports. These could be simple landing pads on rooftops or large, multi-story hubs with charging bays and passenger terminals. Aviation authorities like the FAA have already released design guidelines for these, covering everything from the size of the landing zones to the standards for high-power charging. But the biggest non-technical hurdle is certification. Before any eVTOL can carry a paying passenger, it must pass a rigorous certification process. This is a monumental task because existing regulations were written for conventional planes, not for aircraft with distributed electric propulsion and novel flight modes. Regulators are creating new pathways to certify these machines. The FAA is treating them as a